Okay, so we just went through the process, and now let's look at the basic philosophy behind this whole process. The whole philosophy is often called this hypothetical deductive approach. So the whole idea is that using deductive reasoning, you deduce hypotheses and predictions from theories, and then you use empirical evidence to test these hypotheses. So in the previous examples I was given, my theory is that there's lack of sense of control leads to panic and then there's stockpiling. So the hypothesis becomes, if we using planning to regain sense of control, we will lower how much people want to stockpile. And we have results from the studies, right? So the key is that these empirical evidence, how do they interact with these hypotheses, right? And the key term here is called falsification, which means that these evidence and results, empirical evidence, always trying to falsify the hypothesis. And that's one of the key components of the whole approach, that if you understand that, the approach becomes easier to understand. Now, it's a little bit counterintuitive. I'm going to explain why. So the idea of falsification was proposed by Karl Popper in 1934. And basically the idea is that a hypothesis cannot be proven true. Okay? So they can only be proven false. So in order for a theory and a hypothesis to be scientific, it has to be falsifiable. And we accept a hypothesis or theory temporarily when the attempts to falsify these theories and hypotheses have failed so far. So if our hypothesis planning should lower the intention of stockpiling, and instead we found that there's no difference between the control and experimental group in our experiment, then this result will falsify our hypothesis, okay? And therefore question our theory that whether it is about the sense of control or not. A little bit more about this falsification and falsifiability, because it is one of the key philosophical idea in empirical science. And the different disciplines in empirical science all follow this kind of logic groundwork laid down by Karl Popper. So he argued that falsifiability, the concept, is that the quality of a statement has to be inherently disprovable, okay? Which means that it can be contradicted with a single instance of contradicting evidence. So if you say the statement is the sun will always rise, and if one day the sun doesn't rise, then it falsifies the statement, right? And notice that it is not about whether the sun rises or not. It is more about the statement itself has to be able to be proven wrong, okay? So it has to be able to be contradicted by some kind of evidence. We have to be able to imagine what kind of evidence can falsify this particular statement, right? For example, another example, if we have a theory says all swans are white, right? Which gives the hypothesis that if it is a swan, then it is white. Then if we observe a single instance of a black swan, then the whole theory and the hypothesis is falsified, okay? So back to the idea of falsifiability, the statement that all swans are white are falsifiable. So Popper said that basically it's impossible to prove a theory true, right? If we keep observing a white swan, we can never prove that the theory to be true, because you never know whether there's a black swan out there. You never know that whether there will be a black swan in the future. So instead of proving a theory true, we should try to prove theories false. Okay? And good theories should expose themselves to falsification. Okay? So the best theories, according to Popper, is that so very easy to falsify, which means that the theorist, person who proposed the theory, already think of all the ways that these theories can, his or her theory can turn out to be wrong. Actually, the theorist himself or herself will actually specify these are the ways to to falsify my theory. And yet, all the attempts to falsify these theories have failed. Okay, that's the best kind of theory, which means that they have only been supported by evidence up to now, and people just hasn't been able to fail them, to falsify them. So one example, which is a very classic example, is Einstein's theory of relativity. Right? So what happens is that before Einstein, there's Newton's theories of gravity and all that, and that explains everything about that physicists were able to observe. Like basically the movement of planets and interstellar movements, that kind of evidence, right? So it has been running all right for about 200 years. But then there's some new evidence that suggests that there's a slight deviation in the movement of these planets, or the stellars, that kind of deviates from what the Newton's theories would predict. So we have contradicting evidence, right? But the thing is that there hasn't been any new theories able to explain these new evidence, right? So there's an incongruence, but they come up with some kind of smaller theories trying to make modifications to Newton's theory, such one of the theories is that assuming there's some kind of an ether wind going on in the universe. And so they come with small modifying assumptions or theories on top of Newton's theory, trying to keep it going, right? So these theories hasn't been doing so well, has been falsified as well, right? But again, nobody came up with a new theory until the Einstein was able to come up with his theory of relativity, which basically explains the new evidence and also explains all the evidence has been accounted for by Newton's theories. So, and also the Einstein theory make predictions as well. So in fact, it has been making predictions up to 2019, where his prediction has been corroborated again with the new latest evidence about the black hole. So his theories of relativity not only explains the existing evidence, but also were able to make predictions about the future, about making predictions that can be falsified, but hasn't been falsified so far for 96 years. Okay, so that's a classic example of how theoretical progression happens in a discipline that is theoretical physics. So based on this logic, right? So what the scientists are actually doing, are they're spending their time to testing established theories to see if it contradicts with new observation, right? And if not, if the new observation fits into existing theories, they find it boring. If it does contradict with new observation with the theories, then there's the new science, and that's how Einstein came up with his theory. And so far, like physicists, or especially like physicists who study cosmetics and cosmics events, must find it quite boring, because none of their new evidence so far has been all of their new evidence still being explained by Einstein's theory. So they must find it kind of boring. The other thing is that if you have some kind of alternative model, right? Let's say somebody came up with a new theory about gravity, but these models do not make any new predictions. If you cannot make any new predictions, then your models, nobody will pay attention to these models. So that's why all these like a layman psychologist, like a layman physicist, or I don't know, there must be a term for them, you know, like I don't know, wheelchair physicist or amateur physicists propose all these like grand models saying that they have reinvented the wheel, they have new theory of gravity, and they when nobody pays attention to them, they kind of complain. But the fact is that usually their new theories cannot make any new predictions. So if you cannot make any new predictions, it's completely irrelevant to scientists. But if you make a theory that can explain previous findings and can make new predictions, they find it exciting as well. Okay. So what happens when new evidence contradicts the established theory, right? So what ideally happens is that when there is a new piece of evidence, when there's a single piece of evidence that contradicts the theory, that the theory should be thrown away. But in reality, it's not the case. As you can see, with Newton's theories, it stayed around for about 200 years, even with new evidence coming out that doesn't fit the theory, because people don't have new theories to replace that. So what happens is that, first of all, people start to question whether the evidence is real or not, right? So is the evidence solid? Is the evidence, the new evidence has to be evaluated. Basically, by evaluated, I mean replicated independently from different labs. Okay, so if multiple labs were able to independently establish that this new evidence is real or is solid, then people started to look at, does the new evidence actually contradict the theory? Remember, there are layers of protection that goes from the theory to the evidence, right? So there's the data, right? There's the sample that you used, the measurement that you used, the method, right? So people started to questioning all these elements, saying that, oh, perhaps you just have a measure that's kind of not accurate, or your sample is biased, that kind of question, right? So people are just trying to protect the theory. So even if that fails, then people will still have to look for a better theory, right? You need a better theory to replace the old one. Otherwise, it creates chaos. So you can see that it's a scrap or fix kind of situation. For example, for Newton's theory, people trying to protect it or trying to add these little assumptions to it to make it continue to work. Okay, so only when everything failed and when there's a new theory came out, do people replace the old theory with a new theory, right? So that's how science progresses, right? You have evidence, but what really is the heart of the progression is different theories. Okay? So some of you might ask, right? So this brought up all kinds of questions, because what I'm basically saying is that we are trying to falsify, like trying to prove theories wrong, right? So people will ask, what does that mean for the term fact? Scientific fact. What is scientific fact? Now, scientific fact is best available theories, right? And these theories are also revisable. So these facts are always waiting to be revised. And the other way of looking at scientific fact is just empirical evidence, right? So the results can be often considered as facts. For example, if you have some kind of a COVID-19 data out there, people consider that's the fact. But earlier, as I mentioned, that if you understand how these data are produced and how these measures are the process of producing these data, you would realize that calling them fact is a little bit problematic, but you would rather throw that term away and look at each steps of this data production process to understand what's really going on, right? So the other question is that how do we get to the truth, right? So because in science we are trying to get to the truth, but now what I'm saying is that what Popper is saying. What I'm saying is that we're not trying to find errors, right? How do we get to the truth by finding errors? So there's this neat analogy by just making of a sculpture. So making of a sculpture, you're doing so by chip away the part doesn't belong to the sculpture, right? So you started with a rock, and you chipped away everything that's not the truth, or chipped away anything that's not wanted, and then you ended up with a product that you can call that's close to the truth. So that's how this can be explained. Popper also, a very important use of this falsifiability idea is that he insists that the boundary between science and pseudoscience is basically falsifiability. So basically, pseudoscientific theories are usually unfalsifiable, which means that they contain claims that cannot be proven false. Okay? So about these theories, like pseudoscience, conspiracy theories, is that it utilizes this kind of a psychology that when something is impossible to prove wrong, then they replace it with the notion that it is true. Okay, but we all know that this is not the case. That just because it is impossible to prove something wrong doesn't mean that it is true. Okay, so for example, the term that there are aliens in the world. Now, this is this falsifiable, right? So it is not falsifiable because basically it requires inexhaustible research for the absence of aliens. Okay, and if you don't find aliens, people can always come up with ad hoc explanations of why you have failed to find aliens, such as government hide them, they cannot be detected by human equipment. Basically, they're saying that they are aliens. So this statement is impossible to prove false, but that doesn't mean that there are aliens in the world, right? So in order to make it falsifiable, we can just say that how about there are no aliens in the world? This is a falsifiable. All you have to do to falsify it is just to show me a case of aliens, right? So one alien can falsify it. So and now I choose to believe in this one because it is falsifiable and it hasn't been falsified so far, right? So yeah, often it's a matter of choice of what beliefs do you choose to adhere to, and it is usually helpful to to stick to the beliefs that are falsifiable and hasn't been falsified. Okay. So this is the idea of falsifiability. Now, there's some common myths out there about what Popper means, right? First of all, a lot of people would ask, okay, so does it mean that science only involves falsifiable ideas and non-falsifiable ideas have no place in science? And actually, Popper himself has explained that. They call these non-falsifiable ideas metaphysical program of research. Okay? For example, Freud has come up with these ideas about subconsciousness, ego, and all these psychoanalytical ideas. And none of them are falsifiable. But his ideas help to give birth to modern theories of implicit cognition and unconscious bias in psychology that are more falsifiable, right? So these ideas themselves are not falsifiable, but they help to create falsifiable systems. And also philosophy and math are both non-falsifiable systems, but they are both critical for science, especially math, right? By giving some kind of a model that science can use. So the second myth is that if the whole paradigm is based on a deductive logic, so does inductive logic, which means from observations to theories, have a place in science at all? The answer is still yes, because induction can be used to generate new theories that are falsifiable, can be further tested. For example, this is Piaget. He's a very famous child psychologist. He came up with a theory of cognitive development by observing children, right? So by observing his own kids, actually, he came up with a very influential theory, and then that theory turns into some other theories, give birth to other theories that are falsifiable. So I was going to take a break, but we're not going to take a break because we took a break earlier. We're just going to continue with the lecture. Okay, so before I continue, I just want to ask are there any questions about this so far? I see some about what I have just described. I mean, the whole section was just an overview about quantitative research process and this whole deductive approach, hypothetical deductive approach to empirical research. Okay. All right. So if you don't have any questions, I'm just gonna continue. Is this related to the so-called null hypothesis? Someone asked. Null hypothesis is a term that's used in statistics. So and we'll come to that a bit later. And yes, in the null hypothesis testing paradigm, they created a null hypothesis that can be falsified. Yes. But the null hypothesis is a term for that used in statistics. So, but before, okay, so what I've talked so far is mostly about, we haven't reached the statistical part yet. We're still talking about hypothesis in a more like a conceptual kind of sense. Okay. Okay. Any other questions or? Okay. So, and also I've shown you some hypotheses earlier, right? So there will be differences, for example. That's a type of hypothesis, and the null hypothesis would say there is no differences. So they create two options of a hypothesis. One is null hypothesis, the other is alternative hypothesis. And by statistical procedure, we can decide which one to accept. Okay? So that's a better way of describing the whole null hypothesis testing, significance testing paradigm. But we'll talk about that before in the third lecture, where I got into a bit about hypothesis testing. Okay? All right, so now we go into data. So the first fundamental concept is the idea of distribution. And so the first concept is variable. So the variable is an element or a feature or factor in the real world, okay, that is liable to vary or change. It has the feature of variability, which means that it can change or take different values. Okay? Now, these values are assigned according to certain procedures or certain rules. Okay? So, for example, a thermometer assigns values, give you readings of the temperature, okay, based on some kind of physical process that's going on. Okay? Or specifically, the volume of the liquid will expand when temperature rises. Okay? Now, so and there are other. So the development of thermometer is a very interesting case, right? So at the beginning, you can imagine that thermometers may not have these not numerical readings, and all they have is like a high or low, for example, right? So then they started to think about, what if we give some specific, try to correlate those values into some real world event, right? So especially for Celsius, right? So the Celsius value of 0, we know that it's the freezing point of water at a certain at the altitude of 0, I think, right? So and what you can imagine is that people who developed this decided to correlate, you know what I mean, to correlate these readings, these changes of these readings on the thermometer with some kind of real world event. So 0 is the freezing point, 100 is the boiling point. Okay? So by doing that, you assign values to that scale, to that variable, and also correlate those values to real world events. And then later, as our understanding about temperature improves, that we get a better understanding of what those values mean. Okay? And this is a numerical variable. So a variable itself is just a group of numbers, right? So in this case, we have a group of numbers of 0 and 1s. Now, again, in order to understand this variable, we have to understand what the number represents. So it turns out these numbers are a voting intention for the 2020 U.S. general election. So 1, we say we'll vote for we'll vote for Trump. 0 will not vote for Trump. Now the key here is that to remind yourself that each value here represents an observation, and in this case, it is highly likely that these observations comes from different people. Okay, so each observation comes from a single report from a person. Now we don't know how it is collected, so it could be that it's the same group of people over and over again, or it's the same individual over and over again, and his or her opinion about Trump just changes all the time, or it could be that each number represents an independent person, and this whole variable is taken, it represents the voting intention at a specific time, right? So if everything is collected at the same time, this is called cross-sectional data. Okay? And as I said earlier, it can take different values, right? Either 0 or 1. So the variation happens between 0 and 1, right? So and the variation is that the variability idea comes from it can take the value of 0 or 1. But it doesn't have to. It could be that everybody will vote for Trump, that there will be no variation. Everybody is a 1. But everybody will not vote for Trump. There's all 0. That there's no variation. But there's a variability because it can take one or the other, okay, values. And here's another numerical variable. It's basically a vector containing different numbers, right? And imagine that what these numbers mean is the days of depression before entering hospital treatment. So we have depression, those people who went to hospital for depression treatment. And these are the days of depression before they went into treatment. And again, each value represents that there's variation, okay? There's variation in the sense that some people have longer days of depression before going to treatment. Some people have shorter days, okay? Now, to get an idea about this, if we treated this as a whole group, now to get an idea of this, how the whole group is doing, it doesn't make, it's not very helpful to just look and stare at a bunch of numbers, right? And we have to depict this variable in a way that makes it easier to understand what's going on for this particular sample. Let's call this a sample, right? Now, these are variables, but they're now in a data set, okay? So, and as you can see, that this is a little bit more complex, so in that it is not just a group of numbers, but it's now organized in a way, in the form of a table. Now, on the top of the row, you can see that those are the name of the variables: gender, age, weight, height, smoking, and race. And each row represents a patient, right? And the patient have values on every single of these variables. So now, the first thing I want to talk about is there are two types of variables here. One is categorical, right? So that's just gender. So you can take a value of male or female, and there's no order here. There's no quantity here. It's just like M and F just indicates group membership. Okay? But there's another kind of variable that is a quantitative variable, such as weight and height. This variable takes the form of continuous numerical values. It's not really continuous, but like successive. And these numbers have certain meanings, such as 175 is larger than 140, right? 69 is larger than 59, so we know that someone is heavier than the others, and someone is taller than the others, right? So there's kind of order going on, and other than order, there is also quantity going on, right? So, for example, 0 weight will be the absence of any weight, right? And 0 height will be the absence of any height. So we can also say that somebody who weighs 180 is twice as the weight as someone weighs 90, right? So you can do a lot of more of these calculations with quantitative data, okay? So with categorical data, all you have is group membership. Another key thing that I want to point out here is that on each row, the data is now locked. Okay, so for patient 1, it's always those observations. So if you reorder the data, you have to reorder the whole row. You cannot reorder the cells, right? So in order to make sure that these are still correspond to the same patient, right? So each patient here is now called a unit of analysis, right? So and in this case, each person is a unit of analysis here. Okay. We can also see variability, the idea of variation of variability at the different levels of analysis. Now, I will share with you a data set right now on Microsoft Teams. I would like you to open it on Excel. Let me see, how do I share data? It is also available on the course team channel, but apparently that's not available right now. Let me see if I can just attach that to you and you can open it on your computer. And again, this is taking much longer than it really should be, but let's hold. Okay, so now I'm sharing this Excel spreadsheet with you, and you can download that, and so you can download it and open it up. Okay, so I'm going to open it up on my computer, and I'm going to show you what it is. I'm going to share the screen with you on my computer so that you can see it. Okay, so now you see it on the screen. This is the data set, right? Okay. So this is the data I just downloaded from the website of. Where is it located for us? It's in the. Can you see it on the? Oh, sorry, I didn't send it. Okay, now it's sending it. Now it's sending it through a message. It's in the message. And again, I just found out more and more about how team kind of is bad for this kind of teaching anyway. So okay, you should be able to see it now, right? Okay. Okay, so download the data set and open the data. And you will see something that I showed you on the screen. Try to make it bigger. So you see that there are different sheets in the data. Okay, so there's the first spreadsheet. Should be able to download the data set from. You see it from the message that I just sent out earlier. I'm gonna upload that. Is it message to everyone? I don't know. So you still can't see it. Okay, I'm gonna send it again. It's strange that it doesn't send it to everyone. Okay. Email attachment. Let me just give me a second there. Oh, I got it as well. Okay, will you be able to? Yeah, you should be able to get the message. And earlier you have to find it somewhere. Here. In SharePoint. Let me just pause the recording for the. I'm gonna stop recording for now. I'm gonna